Hi everyone, Mr. Ford here. This video is about the homework for circular motion, the textbook questions and misconceptual questions from the Giancoli textbook that you guys requested that you wanted some additional review on. So I'm going to go over those. So number 5, we have here a child on a sled comes flying over the crest of a small hill as shown in the figure below. His sled does not leave the ground, but he feels the normal force between his chest and the sled decrease as he goes over the hill. Explain this decrease using Newton's second law. So I'm going to jump over to a program where I can kind of draw here. So he's going over the hill. So we definitely see our circular kind of motion here. So that if he's up here, don't laugh at my drawing, that's our sled. So the net force needs to be going downward. So that net force is usually, or in this case, mostly due to gravity. So really, he doesn't really need any net force, or sorry, not net force, any normal force going upward to be able to move in that circular path. So the faster and faster he goes, the less and less that normal force will actually be because of Newton's second law for circles. So as he's going over this, I have messages. As the velocity increases, that centripetal force will also increase, needed to pull him down in that path. So as he goes over, let me go back to the actual question because I kind of forget it. Number 5. All right, so as he goes over at the top of that hill, like we said, under normal conditions, if he's like he is in the picture, just not moving, he would feel, his normal force equal to his weight. But since he's moving over it, his normal force only needs to be less than that, all the way to 0, to move over the top of that hill, because it's really his weight or force due to gravity that makes him go over that hill. So if he were moving too fast, that normal force would be kind of negative, meaning that he would leave that hill and he would kind of jump up in the air and jump over that, whatever it was, past that hill. For number 6, sometimes it's said that water is removed from clothes in the spin dryer by centrifugal forces or centrifugal force, throwing the water outward. Is this correct? And discuss. So we mentioned the centrifugal force before. So if this is like a top view of a dryer, some dryers are actually, actually most dryers are side fed. So if this is like a side view, where you have all your clothes in here, and the dryer spins in, do I know which way direction my dryer spins? I'm not really sure. Let's just say it spins clockwise. So the clothes are going to go clockwise. The clothes want to move in a direction tangent to their motion. So like, let's say this, center of mass of that shirt right there is going to go, and it actually wants to move in this direction. But it's the side of that dryer that prevents it from doing so. So the clothes are forced to keep moving in that circular path, but there's holes in the outside of that dryer tub, which allows the water to fly out. So that's what they've in the past have referred to as a centrifugal force, meaning the force that's causing the water to move outward, but it's not really a force, it's a fake force. It's actually the inertia of the water droplets within the clothes They keep on moving in the direction that they are at that point. And it's the centrifugal force, the real force, that would cause the clothes to stay moving in that circular path. Since the clothes keep on moving in that circular path and the water separates and their inertia keeps moving outside of it, that's what allows the clothes to dry. And of course, you have the heat involved as well. To kind of accelerate that drying process. But as far as the first part of it, really in the washer, this happens as well, to get during that spin cycle. So that was 6. I think we answered that. So yeah, so we weren't looking at necessarily a spin dryer. So it's kind of confusing. There's a spin cycle on the washing machine, but also dryers work on spinning as well. So the next question you guys had was number 8. We have a bucket of water being whirled in a vertical circle without the water spilling out even at the top of the circle when the bucket is upside down. So this is something that you may have done as a little kid at the beach or lake or pool, where you fill up the bucket full of water and you spin it around and the water doesn't fall out. So the concept there is very similar to what we've been talking about. So if this is you kind of spinning that bucket, don't laugh at my drawing. It's a big bucket. And you have some water inside of it. And you're spinning this around in a circular path. So the water at that point that is drawn wants to move out tangent to its motion at that position. But it's really the normal force. Angles aren't necessarily accurate in the circle, but it's the normal force provided by the bottom of the bucket that's keeping the water moving in that circular path. So if we move or spin the bucket in our circle, our vertical circle, too slow, there's not going to be enough force to cause it to move in that circular pattern, and it's going to fall and you're going to get all wet. So the velocity and the force, which in this case is provided by the bottom of the bucket, it's the normal force, are proportional. So as the velocity increases, so does that force. If you don't move it fast enough, that force will reduce to 0 or really negative, because it's kind of a net force, where gravity is downward. So if there's not enough normal force, and that force starts to not, be enough to allow the water to move in that circle, it will fall down. Then we have number 9. So astronauts who spend long periods in outer space could be adversely affected by weightlessness. Like you get weak, so kind of if you've been sitting in a bed long time, your muscles are not being used, so they get weak. One way to simulate this is to be in this scenario that is pictured, and it spins around, simulating gravity. So really when we walk around Earth, or we're in a car or some kind of ride or amusement park ride or roller coaster, we don't think of gravity. We usually think of normal force, right? How much force is pushing up by the Earth, and that's what that's what scales measure. They measure the normal force. So we can easily see this by if you step on a bathroom scale and you push up on the counter with your hands, your weight will read less. Really, it's not your weight; it's your normal force. Or if you pull down on the edge of a counter, it will read that you weigh more, but really it's your normal force because our weight does not change. So in this scenario, the astronaut spins around and around and around, where they experience a normal force, which they don't, no pun intended, experience a normal force, because normally they don't have that in space because there's nothing supporting them, because their weight, their gravity is less than they're used to. So this simulates not necessarily gravity, but it gives them a normal force. So a couple questions. Part A, how objects fall. So if we're standing on Earth and you drop something, it's going to fall directly to your feet. In this scenario, though, let's imagine real gravity is straight down. Let's say they're directly above the Earth and there's no other planets close to them. If that astronaut in the green shirt dropped something, it would fall straight down. Let's say he was in one of those beds. If you drop something, it will still fall straight down, or it will move kind of in a projectile motion type pattern or path, because we're moving in a circle. It's simulated gravity. So object will fall still straight down compared to our picture, but they're still moving, so it might be, depending upon when they're released in this circular shell, it will follow the rules of circular motion, or not circular motion, projectile motion, because they're moving both potentially in the horizontal direction and also vertical direction. So they might go up and then fall back straight down below where the chair is and the potential astronaut in the green shirt. For part B, the force we feel in our feet, that's going to be the normal force, which is this centripetal force. So if we assume there is no gravity whatsoever, which doesn't really happen, it's really only the normal force, or what we're really feeling is the net or overall force, the difference between normal and gravity. And see any other aspects of gravity you can think of. Don't really know what I mean by that. Explain how this simulates gravity. Consider any other aspects of gravity you can think of. So I think it really means, without looking at the answer key, that even if the astronaut was not moving, they would weigh less in space because of that whole universal gravitation concept we talked about last time. So really, depending upon how far they are out in space, even though they do have a little bit of weight, a little bit of force due to gravity, it would be insignificant and they're not used to it, so they feel weightless. Let's say 10. We have a car going over a series of hills and valleys at a constant speed. So we're looking at circular motion, and we're given a radius given by capital letter R, and at which point A, B, or C is the normal force acting on the car. So at all points, there is a normal force. So where is part A, the largest normal force? So it's going to be part C, or position C. So if we look at like a picture of that, so we have like A, B, and C. When we look at our circular kind of motion, part B, there is no circle. So at part A, our force diagram would have to show that the net force or centripetal force would have to be mostly downward. So we really would only need a little bit of normal force, or no normal force really, to be moving in that circle. At position B, gravity and normal would have to be equal. I labeled that wrong. And then at position C, if I drew gravity right, normal force would have to be larger than gravity. So at position C, since the center of that circular turn is above the position of the car, normal force would have to be greater. So then the smallest, it would be at A, as we've seen in that picture, because we really don't need any normal force to go in that turn. So we could just be happy with, the weight of the car going down, which that's when you usually feel that kind of weightlessness feeling or queasy feeling if you're in a car or roller coaster and you go over a little bump like that. When you start to be at the point where you don't need any normal force to cause you to go around that little bump in the road, that's when you feel that kind of weightlessness feeling or queasy feeling in your stomach. So that was B. C, where would the driver feel the heaviest? Again, feeling is usually associated with normal force. So we would feel pushed down into our seat. So this is where that centrifugal force kind of came into play years and years and years ago, because you felt heavier at position C, but there's no real force causing you to go downward. We're just experiencing, the seat pushing back up on us, so we're associating that with how heavy we feel. So the driver would feel the heaviest at position C and lightest at position A. How fast can the car go without losing contact with the road? At A. So if we look at A, really we don't really need the rest of that. So force diagram for A. I kind of forget the question. So without losing contact with the road. So we're looking at the borderline where normal force would be 0. So we're saying normal would be 0. So that's the borderline. So looking at centripetal force, where really we're looking at Fg equals mv squared over r. And we're going to celebrate because everybody's going to bring mass to this party for this problem. So everybody gets a little bit of mass, so we can take mass from everybody. And to find out that actual speed, we would then just solve for v, meaning square root of whatever g times r would be. And again, we're looking for that boundary to where there would be no normal force going over that hill. Let's see, 10, 11, 12. Why do airplanes bank when they turn? How would you compute? That's a weird term. The banking angle given the airspeed and radius of the turn. Hint, assume an aerodynamic lift force acts perpendicular to the wing. So this is kind of what we saw in the packet, or they're referencing example 5-7, whatever that means. So force diagram wise, if the airplane is going to make a left-hand turn as it's approaching us, that means that lift force would go up and to the right. And this is starting to look very similar to something that we just did. So we have the lift force, provided by the wings going up and to the right. It's going to make like a rightward turn to where maybe this is like the center of the turn, and this is the axis that's moving, just like our flying pig lab. So where the y component of lift would equal the weight of the plane, and it's going to be the lift force in the x direction that's causing it to move in a circle. Let's go back to the question. So we're looking for why do airplanes bank when they turn? And it's because it's the lift force that's determining, where this airplane goes. The airplane can use its rudder to kind of change the direction of the plane, but it's not going to turn it per se. It'll just go sideways and continue to go forward, or spin out in a circle. So they need to bank or angle themselves so that they can turn. So we're looking for the angle here. With an equation here. So we're trying to figure out what this angle is to get some desired turn. So it's a Newton's second law for circles problem, where that centripetal force is determined by the x component of gravity only. And that x component of gravity would be, Fg equals mg. So we're looking at the cosine theta of whatever gravity is. Or I'm sorry. We're not looking at cosine because we don't know lift force. I don't believe. Let's take a look. What do we know? We only know the speed and the radius of the turn. So we're not looking at cosine. So we know the y component is going to be equal to gravity. So I'm going to step aside here and do some trig. So tan theta is opposite over adjacent. So the opposite side from theta is mg. The adjacent side is FLX. So FLX is equal to, if I do some manipulating, let me plug that in. Yet again, we have a mass party. So we get g over tangent theta, v squared over r, and we're looking for theta. So if I can do my trig right, skipping a step. So I believe I did that right. Inverse tan of whatever acceleration due to gravity is, radius and velocity squared would give us our angle for banking at that radius and then that speed. But double check me in the solutions in Schoology to make sure all my trig and math is right. That was 12. Then we get 19, 22, and 23. 19 says the source of the Mississippi River is closer to the center of the earth than its outlet in Louisiana because the earth is fatter at the equator than at the poles. Explain how the Mississippi can flow uphill. So this is the concept we're looking at. So the earth isn't perfectly round, right? It's kind of looking like this. This is a little extreme. So if this is the flow of water, right? a little bit further down. The Mississippi doesn't go at the equator, but you get the idea. So this might have like a, this is higher in altitude, this is lower, just because of the thickness of the Earth and the way that it's spinning. So that means that the water somehow flows uphill. So how is that possible? So we got to think in terms of forces. So like forces are making this flow. So it's really the force due to gravity that's making it flow. So anytime you look in chemistry, physics, science, things tend to go from higher to lower, whether it was higher pressure to lower pressure, or more gravity or higher gravity, gravitational pull, to lower. So when we look briefly at that equation for universal gravitation, right? So we're looking at, the mass of the Earth is the same, the mass of a droplet of water is the same, g is the same. What we're really looking at is the radius. So given, at the start of the Mississippi River, you might have a smaller radius, and then at the outlet of it, it's a bigger radius. So when we look in terms of relative sizes of force and radius, the bigger the radius, the lower the gravity. So at the start of the Mississippi River, you're going to have a bigger force of gravity, and then at the end of it, that same droplet is going to weigh less. So you're still going to have that force pulling it down towards the end of that river. So it's actually still going uphill. So it's a weird concept. And it has to do with the fact that the Earth is wider in diameter, right from the core, the center of the Earth, to the surface. So there's less gravity. So it weighs less, and it's going to be pulled towards the end of that river or body of water. '22, the massive planet Pluto was not known until it was discovered to have a moon. Explain how this enabled an estimate of Pluto's mass. So we're still dealing with Newton's law of universal gravitation. So through some other math and other physics, we've known the mass of the Earth. But now we're looking to find Pluto's mass. So through some simple observation, we can determine the radius, right? We can see its orbit. We can track that through the sky. We can also estimate, based upon the motion of the moon and the planet and other planets, the force required to do so. We also know the mass of the Earth from other observations. And then g is a universal gravitational constant. So if all of a sudden we see the orbit of a, sorry, this isn't the, I was wrong here. The mass of the Earth, but it was the mass of, was it the moon or Pluto? Okay, so it's annoying. Where'd it go? Here you go. Would be the mass of the sun. Sorry, because because Pluto is not orbiting, the Earth. It's orbiting the sun. So the issue is, using this equation, the true mass of Pluto wasn't known because we matched up its radius, its gravity, based upon where it was, and it wasn't actually correct. And then we discovered that it has a moon, which would then add mass to its orbit. So if you imagine this is the sun, this is Pluto, and this is its moon. So at some point, we didn't talk about center of mass yet, but whatever the center of mass is, it would be off of the center of Pluto that orbits the sun. I know it's not a perfect circle. So previous estimates of Pluto's mass were wrong because we didn't incorporate the mass of its moon. And then we can get that total mass based upon this idea, and then we can focus in on just, I don't know why that doesn't right, just Pluto and its moon, and look at the orbit of that. So using, sorry, I was on the same thing, this idea, along with some other measurements, which you're like, well, Mr. Ford, how do we know the force? We don't really know the force as a number because you can't put a scale up into space. But what we can do is think of a force diagram. What is the only force that's causing this centripetal motion? It's going to be gravity. So what we can do is say, Fc is the gravitational force. So then we start to do this. So where this is the mass of, we'll just say Pluto for argument's sake. Well, let's just do the moon. Pluto's moon. I forget what they're asking us here. The moon. So G they can look and track the motion, the velocity, and the radius of Pluto's moon. You can start to see that it's going to be a mass party for only Pluto's moon. It's only a mass party for Pluto's moon. And I wrote that wrong because we're looking for the mass of Pluto. All right, so seeing Pluto and its moon's orbit, they can fairly accurately track the circumference of that, the radius of that. They can time it so they can get the velocity and the radius, which you can see one radius cancels out. It's a mass party for the moon. And they can accurately solve for the mass of Pluto just by tracking its motion in the sky. And I think one of the last ones here. '23. The Earth moves faster in its orbit around the Sun in January than in July. Is the Earth closer to the Sun in January or in July? Explain. Note, this is not much of a factor in producing the seasons. The main factor is the tilt of the Earth's axis relative to the plane of its orbit. Okay, so looking at this. Sorry, just a second. This is 23. So we got Earth, no, Sun, Earth. I know that's not relative size, right? So if that's the Earth orbiting the Sun, that would be a wrong statement because the orbit is not perfectly circular, or it's not a perfect circle. It is circular, but it's more of an ellipse. So what we have to ask ourselves is, how is that ellipse shaped? So I apologize if this is a little bit more skewed one way than the other. Not too bad. So if we have the Earth here versus here. So the question is, when is summer? When is winter? So how do the seasons align? Sorry. And the hint was, don't think of seasons as far as that they mentioned. It doesn't make sense. This is not much of a factor in producing the seasons. The main factor is the tilt of the Earth's axis relative to the plane of its orbit. I'm trying to think the best way to explain this. So we're not looking at the tilt, because the tilt, obviously, when you're tilted closer to the sun, it's going to be warmer, right? So we're ignoring the tilt. So really, there's some more information we need to kind of look at. So the real physics question, aside from the seasons, is really where at position 1 or position 2 is the Earth moving the fastest. So we can look at a couple things. So we got Newton's universal law of gravitation obviously plays a role, but there's no velocity in that equation. But the only force we're looking at, just like the last problem, is going to be gravity. And gravity is, the gravitational attraction between the Earth and the Sun is going to be our centripetal force. So just like before, we're looking at this scenario where, one is going to be the Earth, one is going to be the Sun, and we're looking at the Earth moving. So the Earth's mass does not play a role, so that's gone. One of the radius is gone. So we can see if we look at just the relationship between velocity and radius, they're inversely proportional. So when radius is the smallest, velocity is the greatest. So that's the concept to be looked at here, that, when we have the smaller radius, when we're at position 1, which happens to be during the winter, during January. We're not looking at summer or winter. We're just looking at the months of, of January, and where we are in the orbit. So we kind of need some prior knowledge to know that this is January on this side. Oops. Which they didn't necessarily specify. I think they are asking you definitely to look at some other information in the book to see which side we need to be on. They're assuming you have some prior knowledge of that. But the concept there, as long as you know, if you're closer to that smaller radius, that's where you're going to be going the fastest. All right, so there's some more questions of misconceptual, and I will post them in a little bit later tonight.